So this is the last problem. The period t of an oscillations of a mass m on a string having a spring constant k is t equal to 2 pi square root of m over k. The uncertainty in k is 11% and uncertainty in m is 5%. Calculate the uncertainty in the value t of 1.2 seconds. This problem is a little bit challenging. Just pause the video and try yourself before you continue on watching to see the answer. So this problem, we apply the third rule that we learned from the earlier video that summarized the rule of propagations, and this is the rule of to the power. And so we have y equal a to the n, then we have the fractional uncertainty of y is equal to n times the fractional uncertainty of a, absolute value of that. So we know that our measurement going through this calculation right here, and we need to simplify this part in here. M divided by k, I'm going to just call that equal to a. Okay, I'm going to say a equal to m over k. So this equation, then I simplify it to equal square root of a, and square root of a is the same thing as a to the 1/2. By now you're probably wondering, okay, so what happened to the 2 pi? Why does it disappear? Well, if you think about it, in the measure of the variable m and variable k, both of those have uncertainty, but 2 pi is a number that go on pretty much forever. So it has as many numbers number of precisions we want to. So technically it has zero uncertainty. So we're gonna ignore that. You need to propagate zero uncertainty, right? So we just simplify it to this right here. And we know that, see this, if it's in this kind of format, then we use this. I'm just rearranging delta y is just delta t now, because that's what we're looking for. And this is the period. That's 1n is 1/2 because that's n right here, and so we have to bring to the front, so that's 1/2. And then so delta 8 over a. So I'm just recopying what's up here. So how do you find this fractional uncertainty for a? Well, a is m divided by k, and so when we do the divisions, this second rule apply, right? When we do division, we just add the fractional uncertainty of m plus the fractional uncertainty of k together. And the good thing is the quantities were given to us in the problem. 0.11 is the 11% right here. This is percentage uncertainty, so to make it fractional uncertainty, I put it in decimal form. And this is 5%, so therefore it's 0.05. And when you add them together, we give you 0.16 as the fractional uncertainty for a. Then we can just take this right here and plug into here. So it becomes 1/2, 0.16 equal to 0.08. Let me draw a line here to kind of separate the two and clean up this algebra a little bit here. So we have delta t, which is the uncertainty for the period. Then this is the period itself, t, which I multiply both sides, so I bring the t up, see, 0.08 t up over here, and that by itself. And then now I just plug in 1.20, which is a given quantity right here. Multiply that together, that will give us 0.096 seconds for the uncertainty in the period t. And then clean that up, it's just delta t, uncertainty in t is equal to 0.096. And so to write that in, write the answer, I say the period equal to 1.20 right here, plus or minus 0.10 seconds, right? We have to round this up because we know that the precision of the measurement is 2 number after the decimal place. So that's why there should be 2 number after the decimal place. So that is pretty much it for this problem. Have a wonderful day, everyone.